Okay, so now that we've talked about the bolt response, the question then remains is how do we get the bolt response to allow us to create such statistical images that I'm showing here in this figure, and to get the activation maps that we're actually interested in, right? Well, the problem is there are lots of steps, and the goal of the course is to explain many of the critical steps. So there are pre-processing steps, and then there are model creation steps in a sense, so where we create a general linear model, and then conduct statistical analyses on the images that we've acquired. So just to give you an idea of how this looks like, and this is a simplified version that was used in the older ages, here is a processing stream or in SPM, which is the software that we'll use in the tutorials. So first, we acquire a time series of images in the API plane, so T2 star images. There will be some subject movement, which we then need to realign. Then we need to normalize these images. That means we have all these different images from all these different branes and different shapes and sizes. I'll show this in a minute. We have to bring them into a common space, and we call this step normalization. And that allows us to make comparisons across many subjects. And we want a high number of subjects because that increases statistical power. Next, we do some smoothing to improve the signal-to-noise ratio, and then we start model building. So we create a general linear model that is, we make a design matrix with our predicted neural responses, and then we observe how does this relate to the observed neural responses. So the GLM then conducts parameter estimates in the statistical software that are reflecting how predicted match with observed responses. And that allows us then to create statistical maps for each individual. And using statistical inferences and Gaussian random field theory, we can apply to maps of multiple individuals. So we have a first level model and we have a second level model, and then we conduct statistical inference on those. And Gaussian field theory is mostly used to correct for multiple comparisons. So these are, in a simplified form, the pre-processing steps, but we'll go through a few more actually in the tutorials that allow us to work with this data. Speaking of data, let's take a few moments to talk about how fMRI data looks like, what it is, and how we acquire it. So the final data set, the functional data set that we'll work with is going to be four-dimensional. It has a structural image that is acquired using the T1 contrast, and this is the image of a structural image here. Then we have multiple functional images that are acquired using the T2 star sequence. Fundamentally, we are recording 2D slices. So we can think of them as pixels in a sense that are distributed as squares across this box in a typical matrix of 64 by 64 pixels. So 64 going down this way and 64 going across this way. So we have 4096 pixels in a typical image. Now, while we record these slices, so we record them from bottom to top in our scanner, we record multiple of these slices, which can then be reconstructed to a 3D image of the brain. And that's basically a trick to get around the 2D limitation. So we can only record one slice at a time. That takes about 50 to 100 milliseconds to acquire one of these slices. But we do this multiple times, so somewhere between 30 and 40 slices that are acquired per brain. So there we then have a 3D image. And that is true for both the structural image, which is a 3D image, which is acquired by acquiring multiple slices. I'll show this to you in a second. And that is also true for the API images that are the functional images, right? So the main point is here, we have two data sets. We have a structural image and we have a functional, a row of functional images that are acquired across time. Those are two different data sets we'll be working with. Both of these data sets are 3D, but the functional images are also 4D because not only do we acquire different slices to get one volume of the brain, we also acquire multiple volumes of the brain across time. So as the subject is making his or her decisions in the task, every 2 to 3 seconds, we record a whole new volume of the brain so that we can cover the time domain to observe signal changes across time, and ideally with our treatments in the experiment. So relative in condition 1 relative to condition 2, let's say. So this is how it looks like to make a 3D volume. So we acquire multiple slices. So the 3D data is basically acquired slice by slice. There are different sequences again. Some start at the bottom and then acquire upwards. Some start at the top and then acquire downwards. And then there are some that are interleaved, which means you start by acquiring slice 1, then 3, then 5, then 7, and go through all the odd slices first. And then you go back and go through all the even slices first. There are some advantages and some disadvantages to each of these types of sequences. So we have ascending, which is going from bottom to top, and that's the one we are using. We have descending, which is going from top to bottom, and we have interleaved types of slice acquisitions. So finally, it's important to note that there's a timing of slice acquisition, which is important, which is called the TR, or the repetition time, which is basically the time that it takes to record one of these slices, which is in the range of 50 to 100 milliseconds. And we also talk about TR later in terms of how long it takes to record one entire volume, which is an important aspect that you determine in your scanning sequence. So from bottom to top, recording something between 30 and 40 slices to make up one entire brain volume before the next brain volume is recorded. And we can have a look at the slices in this image here, which show basically the progression of recordings from the bottom slice up until the top slice. And you can see how this progresses. You can see the cerebellum here. And then as you move up, you can see the eyeballs in the front. You can see some cortex coming in here. Also, you see the signal dropout in the nasal cavity here, and also the signal dropout on the lateral regions here. And you move up to higher areas where you can then see the ventricles in black. The ventricles here are shown in white. So these are the ventricles here and back here. And the further up you go, the more you can see of the cerebral cortex areas here. So finally, you end up with the top slice here. And this is then summarized into one 3D volume that we have and that we work with. And that's how we make 3D images, basically. So let's go over this again. So from 2D to 3D, at the 2D level, we have each slice providing us basically with a y-axis and an x-axis, and then each image is recorded. Each slice is recorded, but each slice also has a certain thickness, which is typically between 2 and 3 millimeters, or a little bit higher, but those are the typical estimates, which gives us a voxel. So already each slice gives us a 3D unit, a volumetric pixel to work with. And in this pixel, as I said in an earlier video lecture, we have a number of, about 1 million neurons, which is quite a bit. And so this is at the 2D level. Then we record multiple slices throughout the brain and then reconstruct them into a 3D volume. And that's basically then the unit that we're working with. But in the end, we're going to be analyzing individual voxels and their signal changes across the experiment. So this is an example experiment here where the orange parts are the offset of the task and the blue parts are the onset of the task. And you can see that you have increased activation during the blue parts and decreased activation during the orange parts. So this is a voxel that actually tracks quite nicely the task that the participant is doing here. So moving from 3D to 4D means basically recording multiple volumes across time. So we start, let's say every 2 seconds, we record a whole new volume. So the scanner starts at the bottom, records until the top, and then starts again at the bottom. Then this gets reconstructed in the scanner, and you get a new time point every 2 seconds. as you can see here, leading to now a 3D volume being recorded every 2 seconds throughout the entire experiments, which gives us about, let's say, 500 to 1,000 volumes or time points that we can then work with and correlate our behavioral measure with the signal change observed in each of the voxels within this 4D volume. To also show you what an image is, here's a graphical representation of the image. So within just this tiny box here, we have different values that may change over time as the subject is doing the task. And these values are arbitrary units that reflect the intensity of the activation in some sense, but just in some sense also the different tissue types that we have here, right? But as you do the experiment, these values can change. Let's say we focus on this voxel in the caudate nucleus here, and it's a reward-related task, then we might see that whenever the subject sees an outcome of a positive reward, then this signal goes up. Whereas whenever he doesn't or she doesn't see that outcome, then this signal goes back down again. So we observe these changes, which are basically levels of gray or grayscale levels in arbitrary units, but they are our signal because they reflect signal changes across time depending on our experimental manipulations. So this is the image we're working with. These are the units that we're working with here, but we do a lot to these images during the pre-processing steps. Also of note is that there are a number of artifacts that we have to deal with in the scanner. Those artifacts include radio frequency leakages, which you can see here as these stripes that go across the image. They can occur when you have ungrounded electrical connections inside the scanner. For instance, in many of our experiments, we work with electrical shocks that we send to the subject in the scanner, and that could lead to these types of leakages. But obviously we check for this, we control for this, it's quite easily visible, and then we can fix the problem quite easily if we can detect the problems. And we can have variations in the fields, so these are called magnetic field inhomogeneities that we see here, where the center of the image is much brighter than the outside of the image, and that's also something we can check for. And the easiest way to check for this is by using phantoms. So every day before the scanner gets used, the fMRI or the MRI technician is going to do a bunch of quality checks on the scanner. And the easiest way to do this is by taking one of these fluid-filled phantoms, placing it in the scanner where the head usually goes, and then taking a number of recordings from the scanner to see if everything looks as expected. And if it doesn't, then you see images like this, and then you know something's going wrong and you can quickly find the problem and fix it. So there is a lot of quality control going on, and actually that occurs daily at our scanner here. Good, so I'll stop here for now. So we know something about the data structure now that we're working with. We know that we acquire 2D data sets, which become 3D for anatomical images, and 4D because the time component is added to this for functional images. Thanks for your attention.